So welcome to our new topic. It is momentum and impulse, and you can clearly see here the effect of momentum and impulse on a golf ball hitting the wall. So moving on, let's start with everyday language. So what do you say when Crystal Palace Football Club is on a roll? They may not be leading, they may have not scored the goals yet, but you say they have momentum. A team that has momentum is hard to stop. So, what is this momentum we are speaking about? Well, an object with a lot of momentum is also hard to stop. So the equation for momentum is P, which is the symbol for momentum, equals mass times velocity, or P equals mv. And the units are kilograms meters per second. We get the kilograms from the mass and the meters per second from the velocity. And because it is a velocity, momentum has a vector. Because mass is a scalar quantity, you're multiplying it by a vector quantity, you end up with a product which is a vector, which means that momentum has not only a size from the mass, but also a velocity, and so therefore it has a direction. So let's do some practicing. So you have a 1,200 kilogram car and it's traveling west, there's the vector, at 25 meters per second for 3 hours. So what is the car's momentum? So I want you to pause the video now and have a little think about that for about 10 to 15 seconds, replay the video and see if you're on the right track. Okay, welcome back. So the first thing you have to do is identify the variables. So the mass is 1,200 kilograms. The velocity is 25 meters per second west, remembering it has both a size, 25 meters per second, and a direction west because it's a vector quantity, and time is in 3 hours. So for 3 hours is a bit of a red herring. You don't have to worry about time when it comes to momentum. But momentum from the previous slide is equal to mass times velocity. So you plug in the numbers. The mass is 1,200. The velocity is 25 meters per second. So you multiply those two variables together to give the overall momentum of the car, which is 30,000 kilogram meters per second, and also west, because remember, it's a vector, it has direction. So hopefully you got that right. So the next consideration is how hard is it to stop a moving object? Okay, so for those who play rugby, you got this massive prop forward running towards you. How easy is it to take him down in that tackle? See, science, it's relevant. To stop an object, this prop forward, we have to apply a force over a period of time. And this is called the impulse. Okay, so you're applying your force on your tackle, and the time it takes to do that tackle is the period of time. And it's giving you an impulse. And the equation is impulse is force times the change in time. And its units are newton seconds. Again, the force, so it has units of newtons, and you're multiplying it, so time is measured in seconds, so overall units is in newton seconds. And because time and force are scalar, impulse is a scalar quantity. It doesn't have a direction per se, just a size. Okay, so reiterating, F is for force in newtons and delta T is for time elapsed in seconds. Okay, so remember earlier in the course around mechanics, we looked at Newton's laws, and Newton's first law was an object at rest stays at rest unless acted on by external force, and Newton's second law had an equation which was force equals mass times acceleration. Okay, so you can then use Newton's second law and plug it into the impulse equation to give force times change in time equals mass times change in velocity, because remember, acceleration equals change in velocity over change in time. Okay, So that's the equation that we're going to now be applying in different contexts. So this essentially means that impulse is just a change in momentum, because remember that momentum, P equals mass times velocity. So if velocity changes with a mass, you've got a change in momentum, okay? And a change in impulse. So you've got to ask yourself the question then, why does an egg break or not break depending on the surface it lands on? So if you have an egg and it's dropped on a tile floor or the linoleum floor we have in the classroom, it smashes into little pieces, okay? Just like in a nursery rhyme, Humpty Dumpty. He fell off the wall, he had a great fall, and none of the king's horses could put him together again. But if Humpty Dumpty had been dropped on a pillow, he wouldn't have broken. Now, why is that? Well, that's of course because of physics. So remember the equation, force times change in time equals mass times change in velocity, or impulse is essentially mass times change in velocity, or change in momentum. So in both cases, mass and change in velocity are the same because they're both accelerating due to gravity when Humpty Dumpty falls off that wall. But as the change in time goes up, what happens to the force? Right, the force goes down, okay? Just illustrate that here, okay? So if that number goes up, and that's going to be a constant, right? This section of the equation, because the mass isn't going to change and the acceleration due to gravity isn't going to change. That means that in order for that to remain a constant, then the force has to go down. Okay. So as force goes down, time increases in order to make sure that the change of momentum stays constant. So when you're dropping Humpty Dumpty onto a pillow, the egg slows down as soon as it touches that pillow. Okay, a pillow increases the time the egg takes to stop. Okay, because it's increasing in time, the actual force being exerted on Humpty Dumpty is going to be less, so he won't break into 1,000 pieces, and all the king's horses and all the king's men will be out of a job. So here is a practice problem. A 57-gram tennis ball falls on a tile floor. The ball changes velocity from negative 1.2 meters per second to 1.2 meters per second in 0.02 seconds. So what is the average force acting on the ball? So pause the video now, try and work it out, and once you've worked it out, we'll come back and we'll have a look at the answer and see if you're on the right track. Right, so let's see if you got it right. Okay, so again, you're identifying the variables. The mass is 57 grams, or in this case, because we're now converting that to SI units, it's 0.057 kilograms. And the change of velocity is going to be from plus 1.2 minus 1.2. Remember, of course, that change in velocity equals the velocity final minus the velocity initial. And because the initial velocity is negative, it's going to be plus 1.2 minus 1.2. So it's going to be 2.4 meters per second. And the time is 0.02 seconds. Now, unlike in the previous example where time was not relevant to the equation, now it is. Okay, so now we must plug in the equation. So force times change in time equals mass times change in velocity. So force, by plugging in the numbers, force times 0.02 seconds equals 0.057 kilograms times 2.4 meters per second. So you rearrange the equation to find F, and you get F being 6.8 newtons. So hopefully you all got that right. Okay, so this brings us on to car crashes. So let's just test your understanding of the physics. Would you rather be in a head-on collision with an identical car traveling at the same speed as you, or a brick wall? Assume in both situations you are coming to a complete stop. Okay, so take a guess now. Okay, so everyone should vote now. Okay, since if you're working at home, put your finger up as well. Raise one finger if you think it's better to hit another car. And 2 if it's better to hit the wall. And 3 doesn't matter. Okay, so the answer is, drum roll, if you have drum rolls. Okay, the answer is, of course, doesn't matter. Okay, because momentum is based on, or the impulse is based on your mass and your change in velocity. Okay, in both situations, the change in time, mass, and change in velocity are identical. The time it takes for you to stop depends on your car, the mass of your car, and the change in velocity depends on how fast you and your car were traveling initially, not the fact that you're heading into a brick wall or the velocity of the other car. Okay. Let's look at some questions. So a child in a sled moving down a hill at 20 meters per second. As a combined mass of the sled of a child is around about 100 kilograms. Okay. And the momentum of the child in the sled, therefore, is going to be equal to which of these answers? A, B, C, or D? Okay, pause the video now and have a little think about that, and then we're going to go work through the answers. Okay, so welcome back. So what equations do we have? Well, of course, looking at momentum here. So our equation for momentum equals P equals M times V. And the variables we have are that V equals 20 meters per second, all right? And the mass and M equals 100. So plugging those numbers in, P equals 20 times 100, which equals, of course, 2,000 kilograms per meters second. Okay, and therefore the answer is going to be D. Next question. When is linear momentum conserved? A, when it's only nonlinear forces are present. When more linear than nonlinear forces are in the system. When internal forces exceed external forces, or when the net force on the system is 0. Okay, so pause the video now and come back to it in a few seconds and see if you've got the right answer, if you're on the right track. Okay, so welcome back. So remember, in terms of conservation of linear momentum, what we're saying there is that mv1 equals mv2. So that means, that means v1 equals v2, which means that over time, acceleration therefore must equal 0, right? Because if your velocity stays the same over time, acceleration is going to be 0. So, force equals mass times acceleration. So when will the forces equal 0? Okay, it's Newton's first law. When they're at rest or at constant velocity, and v1 equals v2, so that means it's at constant velocity. So it means when net forces of the systems are at 0. So hopefully we all got D. Okay, so this is the last slide for today. So looking at a train, in fact 2 train carriages, and one is at 10 tons and one is 4,000 meters per second. One has 30 tons and is at rest, and then they collide. So the question is, when these 2 freight cars are at different mass collide and couple, what will the resultant velocity be? Okay, so pause the video now and have a little think about that, and then come back if you think you have the answer. Okay, so welcome back. So looking at momentum, okay, and particularly the conservation of momentum, because in conservation of momentum, the momentum of two objects before they collide is going to be equal to the momentum of the objects after they collide. Okay, and the way we can write that is, well, P1 plus P2 equals P1 prime, I guess, plus P2 prime. Okay. So we got to work out this here. So we're told that it's going to be 10,000, because remember it's in tons, times P2, which is times V2, it's going to be 4. Okay, that's P1. Because remember that P equals MV plus 0. Okay, because remember anything times 0 is going to be 0, equals so we don't know the velocity. Very good. We'll get the mass though, because the combined mass will be now 40,000 times some variable x. Okay. So in this case, it's going to be, well, 40,000 on this side, because 10,000 times 40,000 is going to be equal to 40,000 x. So if you rearrange that, it's going to be x equals 40,000 divided by 40,000, which equals 1 meter per second, and that is your final answer. And that is called, or was based on the conservation of momentum. Okay, so what that is basically the momentum before a collision is going to be equal to the momentum after a collision. There we go. So that's enough for today. So I'm going to focus on doing a few problems on it, and so we can master this and all get excellences.